And hopefully you can hear me okay. I'm having a voice today, so bear with me. Okay, great. Go first. Thank you for the invitation. Apologies for the voice. I'll try to keep this short. But happy to answer any questions. Okay, so today I want to talk to you a little bit about the architecture that we use at PsiQuantum for fault-tolerant quantum computing systems. And the key feature of this architecture is that it's networked, use photons, and therefore that's a feature that we rely upon a lot. Just to introduce who I am, so I lead the system architecture team, so spanning from design of physical hardware as well as quantum architectural methods to implement the systems. PsiQuantum is a company, like right now we're about 500 people, we're based in Palo Alto, and with a single focus, we're pursuing photonic quantum architectures for fault-tolerant computing. You might have a lot of news at the moment because we have had some engagements, but I hope that with this community, the thing that will shine is not all of these names and all of these numbers in the slides, but sort of the work. And we have all of the papers listed in our website. I'm also happy to provide any later on. Okay, so the premise of why we focused on photonics is that we have lovely qubits across all domains, and everybody is getting super high fidelity gates and super clean results. Like, and we can get some qubits to work is not the issue. We know that in order to have a utility scale machine that tackles real problems that cannot be solved computationally today, we need to build very large machines. We heard this in the previous talk, multiple papers right now saying and discussing this topic. And so from the perspective of building a platform, you need to think about what are the other elements that might make you fail. If you have great qubits, how might you fail? And you might fail because you cannot manufacture them at scale. And this is, for anybody who has been involved in this is like the labor of hard work and really a pain to go through those stages. There's also the availability of cooling power. Almost all of the platforms require us to cool down our qubit. And although we're not limited by physics here, there's some certain engineering limitations that exist. You can look at one of the biggest cryogenic plants in the world that serve the world's largest experiments. And you could think of going above that, but you're going to have to essentially revolutionize cryogenic engineering on top of quantum computing. So something to consider. Connectivity, which is that we need to be able to interconnect our chips, interconnect our different parts of our computer, regardless of your qubit platform. Nobody's going to fit everything in a single chip. And so how do you do that? And what are the overheads you add to your system once you consider that? And finally are the control electronics. I think we're all very aware that quantum computer does not only contain qubits, it's essentially always a hybrid system with some classical control. And some of that classical control needs to occur with very, very low latency. And I'm talking about, in some cases, depends on the speed of your system. For some systems, microseconds is just fine. For photons, I am constantly battling with our electronics engineers because I always want less nanoseconds. Like I negotiate every nanosecond because every nanosecond makes a difference. So for the talk today, I want to talk about the central role of networking within a quantum computing system that is utility scale. And this is because, again, we're focused on large-scale systems that are modular, and therefore they have a distribution of the functionality across many modules. And so particularly, so this is more focused on photonics, but actually the role of these three pieces that I'm going to mention, they apply equally to With my belief, they apply equally to all of the platforms. And so I'm going to tell you a little bit about how we are solving them, but I think is something worth highlighting. The number one is that, okay, at the physical layer, having modular and distributed architectures requires that, like, you're gonna be having to overcome the determinism, the non-determinism of your operations. And now you might tell me, oh, you have photons, you're worrying about non-deterministic gates. I have transmon or atoms or whatever kind of qubit you have. I don't have this problem. And I will ask you, anytime that you need to communicate with another chip, how do you do it? Because you don't do it by like moving your qubit. You do it by communicating through photons. And anytime you introduce photons in the equation, you have non-determinism. You have non-determinism from quantum dots, from collection efficiencies. Or if your ions are emitting photons, again, you have like this, the non-determinism is there for everybody. Sure, it's a bit higher up for us, accepted, but it's there for everyone. So that's one key piece. I'm going to talk a little bit about multiplexing and interleaving, which is some ways in which how we resolve this specifically for photonics. Networking is also very important at the quantum error correction layer. So we have some results showing that you can also do some multiplexing at the logical level, which is sort of equivalent to doing like a very small amount of post-selection on things that are already fault tolerant to essentially suppress errors even more. So this is combining like the best of both worlds of having both. You must have an error correcting code, but by actually post-selecting on the pieces of that error correction code that you're putting together to perform your logical operations, you can actually improve the performance. And then the other aspect is, we've all been hearing about these new high density codes. Qubit packing is the flavor of the day. Please give me more logical qubits from the same physical qubits and all this. So the cross codes are very bicycle codes, blocklets. It's like a whole, like, some of them are LPC, some of them not. Whole variety of new type of codes that don't have this feature of I'm only communicating with nearest neighbors. And guess what you're gonna need? You're gonna need to communicate with things that are further away, which essentially means that you have to kind of eat a lot of latency, or you're gonna have to enable interconnects. And finally, at the compilation layer, so I was speaking this morning from QA, actually mentioned a little bit about the challenge, the overheads that you get in computation when you have fixed connectivity. And so the way that we have solved this is by some protocols we've called it two-volume architecture, which essentially removes idle computational volume that you often get when you have a fixed connectivity architecture and you're implementing lattice surgery. Okay, so just like we begin with like PsiQuantum architecture is at its core based on this protocol, which we call fusion-based quantum computation. It's sort of a cross between circuit-based and measurement-based, although frankly, like at this point, everybody's doing the same mixture of both because everybody's doing error correction, which is sort of MPQC, and everybody's compiling algorithm, which is sort of like circuit-based. So we're all in the same mode here. For us, like what it means at a physical level is that we're going to be generating resource states, which are small entangled states of a handful of qubits that have some specific structure, and we're going to be fusing them with devices that are very simple. They're just beam splitters with detectors, and that's it. Now, the magic is in exactly what is the protocol that we're implementing, what is the topology, like the internal fusion complex that we are implementing when generating those resource states and fusions, what are the correlations that we are creating, what is the entanglement network that we are creating. There's a lot of very beautiful math underlying this problem, which we have a fault-tolerant team focused on. There's a very nice paper called Fusion Complexes from some of my colleagues I really recommend. But at a physical level, what you do is you generate resource states, you fuse them, And this essentially gives you sort of like similar kind of, you see like we represent this in like sort of like a 3D sort of scheme. And so you can think of whenever we talk about lattice surgery and we take into consideration the time dimension, you see this kind of diagrams, like they look the same as what you would see from Google and from everybody else, right? Like both with basically a similar thing on different physical platforms. So what does it look like when I say, oh, we're gonna be generating some states? How do I generate the states? What is the physics? So what I'm showing you here is an artist's rendition of a slice of our stack. So if you were to take our chips and actually like do a cross section, in fact, I don't have it today, but we have some videos where like you can literally do that for some of our chips. We make like animation with like SEM picture images. So these are the components that we need. So we need photon sources, which essentially allow us to generate single photon pairs through parametric conversion after bump and occlusion laser. We have passives, beam splitters, etc. We have detectors, single photon detectors. And one of the interesting things about this is if you think about like I am the combination of a source and a detector. So how I generate a single photon is I pump like 1 billion photons of pump light into the source, right? I stimulate a nonlinear process. I generate a pair of photons. And what I want my computer to do is I want to detect one of these photons, this special type of photon. And I want it to suppress every other, billion minus one photons that are from the pump. So we do that through like a variety of schemes, like some interferometric, some like more physical. But the other thing that we need to do is like there's gonna be a scatter, like there's gonna be light. We're pumping a lot of light into the system. So you have to shield your detector. So this actually has been a lot of effort integrated with our partners on having structures that really serve what we want. So what you see on the left was like our old platform. We have an nature paper sort of outlining a lot of the results. You see on the right is our newer platform where we have sources, single photon sources that no longer require tuning. Now, why is this important? Because if I need to be a cryo, and in order to tune my source, I'm gonna heat it up. It's a bit of a waste. Like, surely we can do something better from design. And so this beautiful result that is kind of like, there's a specific design for this tuning the source, and it gives you like a lot of tolerance to fab variability heating. We now have also, instead of single photon detectors, we have photon counting detectors. So now we can tell that we have detected either 0 or 1 or 2 or 3 or 4, whatever number. This is non-trivial, particularly not only from the device perspective, but also from the perspective of like the cryogenic electronics. We need to do that. And then finally, we have the BTO switch. So the BTO switch allows us to implement as phase shifts. And the reason that we want this is because the BTO is the material known to man that has the highest Buchholz coefficient, 1000 picometer per volt. That coefficient tells you how well can I translate an electrical signal into an optical phase shift, right? Like the higher the better. Lithium niobate, which is the other material you often use in photonics, is less than 100, probably even less than 10. I'm not 100%. And so why do we care so much about this? Because the higher the number, the shorter the amount of material that I need to use in order to enact any one phase shift that I want. And the shorter the material, the less loss. One thing that we are obsessed with is warline loss. Like literally almost every PsiQuantum, every technical meeting, like we have a reference to like, okay, what does this mean for the warline loss of our photon? How much loss is our photon is gonna have? So it's something that is sort of very okay. So hopefully it works. Nice animation. So the stack starts from like. There's many layers of like different materials that create our chips. Two of them in particular are one of them, the superconducting material, which is something that we have now introduced into global foundries. The second one is barium titanate, which is not only have we, this material was well known, it was studied in thin film, which is when you actually have thin film and not like material bulk. But actually, we have been producing some of this in the large form factor. So we're at the moment like this was actually a high risk for the company because there was no manufacturer of 300 millimeter BTO for the thin films in the world. So we stood that up. And UI asked me, why do you care about 300 millimeter? And that's because the reason that you want to go to a really tier one fab, such as Global Foundries, like we've done, is not because you want to manufacture a scale, which sure, you will do. But the important thing is that opposed to real life, where high volume implies lower quality, like that's not the case for semiconductor industry. Higher volume, the facilities that have higher volume, they also have the best specs, right? And that's what we care about. Okay, so there's, as I said, there's quite a few materials that go into our picks. So from this we take out wafers of material. We singulate the most onto die. So here you see a representation. So what you're looking at here is like one of the parts of the interferometer of the source. In particular, part of what this is responsible for is separating that pump, very bright pump light from the photons that we want to distinguish. And to get you a sense of scale of the suppression that this is doing, which is like close to 140 dB, it's as if you took the Amazon River and tried to find a single drop of blood, right? Like that's the amount of like suppression that we're doing of the light in that system. So it's hard work. I'm not going to say it's easy because it hasn't been, but you can do amazing things with this technology. Okay, so you can see here like some representation. Okay, so picks then get mounted into sub-assemblies. There's some assemblies, they have a combination of photonic integrated chips as well as electronic photonic chips in different configurations. Some of them will be at cryogenic temperatures. These ones in particular represent cryogenic temperatures. Some of them will be at room temperature depending on the use. But then you essentially have a repeatable platform that is put together in kind of high volume and some nice animation. So these things get mounted onto like large cryostats that not only have right now the middle portion is this is one. So this is a blender render, very nice. This is based on an actual CAD that we have that we're manufacturing, right? So just to give you a sense. And and so we have like we're creating these cryo cabinets where we can have areas of cryo temperature. We're like talking about like about 4-ish Kelvin, and then areas for vacuum and room temperature. We would still want the vacuum because we require high stability for a lot of the fibers which we use extensively in the system. And so this is one module, some supporting equipment around. And then like the computer essentially is made up by like copy and paste this kind of structure. Now, of course, I've not talked a lot or at all about a lot of the control, which is what essentially turns this hardware into a computer. But just to give you a sense of like basically what it looks like. So as I said, like this is also like a representation of like from the smallest things to the biggest things in the system. And one of the things so we are an integrated company, meaning that like we are actually developing everything. So we have teams that are working on all of these different areas. I think it makes our work like very complex, but it also means that we own absolutely 100% of the trade-offs of the system. And for a system where standards don't yet exist, and frankly, like a system likely doesn't exist yet, that is a huge advantage. This is actually one of the things where, I don't know, I feel like half my job is negotiating the requirements with everyone, right? Because you want to make sure that all the requirements are achievable, and that nobody's too comfortable, because if we're comfortable, then we're not getting anywhere. Okay, so then let me just talk briefly on multiplexing. It's about overcoming non-determinism. This one is like a very simple idea. Starting with our sources, it's a non-deterministic process, like parameter time conversion. we can tune up a little bit the amount, but like 5 to 10% success rate. Now, what is essential whenever you have non-deterministic processes in your system is that they're heralded, and you know when they have happened. Because if you know when they have happened, you actually can use control electronics to control for it, which is what you're seeing in this picture. Like each run, like only one of the sources will fire, which they will then send some signal to a controller that will essentially change the settings of this is a GMZI, it generates my standard interferometer that allows me to do routing. And that those sort of things in the middle, that's the BTO material that I was talking about earlier. And so you see, like, regardless of which source fires, I always get a photon at the top of the output. So this is one way by like scaling up, like having multiple copies. It's redundancy, really. More copies of one thing allows you to have a non-deterministic thing. And as I mentioned, essentially this is true, like, sure, for our single photons, but like say that you have any other technology where you're communicating across chips, like you're gonna have to rely on some form of interconnect, and there's no reliable 100% fidelity, 100% rate interconnect at the moment. So a second, so it turns out that fiber is sort of like this magical memory for qubits, that it works perfectly as long as you accept that it will be only a memory for a fixed amount of time. So it's not like a random access memory, but if you say like, I only want a qubit to be stored for a specific amount of time, you can actually reduce resources significantly just by using like this. I mean, the losses that they can get today with this optical, like the optical fiber could just go on by, like just no other negotiation is pretty impressive. So this is one way, like essentially you can multiplex in space, more copies, or you can multiplex in time, more times that you repeat something. And if you have a system where the native operations are actually slow, and multiplexing in time is going to give you a computer that's too slow. But when you have something where like photonic operations are picoseconds, right? Then my limiting factor is electronics, which are nanoseconds, and is the reason why I'm always negotiating down on the latencies. So this is for a system as practical as ours, this is good. So it slows down the clock a little bit to give us some extra resources. As I mentioned, a lot of the new codes, non-quantum code across from the left, the blocklets, which is something that we've published recently, they always rely on having non-local connectivity between physical qubits. And so thinking about networking from the beginning of your system design is really essential. Macromux, so this is what I mentioned about multiplexing within the reconnected structure. So this is something that for us it was very natural to think about because we multiplex everywhere, so why not here too? But I haven't seen it actually that much in other domains. And we have seen that, so we've developed like a new family of fault-tolerant protocols that have a very high threshold and emerge when we actually don't require perfect states. What I mean by perfect states is that whenever we think about we're creating a part of a code, we always sort of assume like I'm gonna have all the connectivity, or I'm gonna have like, if things don't work, like sort of not everything goes to hell, but like, live closely. And so actually like being tolerant to fault errors, this is another thing that working with hardware is just so enlightening. Like I am perennially negotiating with our systems team. You always want to do something simple. I'm like, yeah, but like half your things are gonna fail. So you need to still give me more resources, right? Because otherwise the thing is gonna do nothing. Like having this mindset of like failure, things are gonna fail, things are gonna break down. At all levels, like even at the level of your quantum computer, like, I don't know, if we could, like anyone working with a big supercomputer, like not all nodes are up all the time, like we know this, right? So why should we assume quantum computers are different? So anyway, as I said, like we've been exploring this concept in the context of our correction codes, and we have seen that there's like a significant increase that we can get on both the Pauli's and the ratio thresholds using this concept within the regression scheme. And finally, active volume compiling. So this is this notion about, if we're implementing something like less surgery in a fixed code, in a fixed connectivity structure, we end up wasting a lot of resources. So if you look at the image on the left, what we see there is just like, this is, I believe it's an adder, is like one of the most used primitives for algorithms. And so you can see the yellow marks all of the areas where like I am actively doing an operation, and all the red is my qubits are waiting, they're idling, right? So is there a way of compiling my algorithms? Well, number one, is there a way of implementing an architecture such that if I don't have this fixed structure, I can get rid of the red area? Because that would significantly reduce my resources. And in fact, there is. So this paper from one of our colleagues on active volume, which essentially gives us a very significant speed up. For example, it's like a 43x speed up for just 48 bit factoring without like no algorithmic improvement, nothing else. It's just essentially just imagine that you never have to wait. Like even in your computer, like when you're running something, your laptop is like shuffling in memory and things like this, right? If you don't have to do that, you don't have to wait, like you speed up just by removing that. So that's, and specifically for this, how do we enable this? So this is enabled by having the possibility of enacting non-local connections across entire logical qubits and logical patches. So as I said, I wanted to keep this short. I succeeded, but okay, so the things to consider is that there are multiple advantages of thinking about networking in the context of quantum computer architectures, particularly of using optical interconnects, which they're the only flying qubit we have, right? Good. It lands at like 3 different layers. However, like one word of caution, I think there's no freelance as we heard earlier, right? They have to be really good interconnects. And what I mean by really good interconnects, it means that like we have to be operating at the right wavelength in qubit encoding. So that magical thing, optical fiber I talked about, is magical at 1550. Don't try it at 900, right? Like it's not gonna be as good because it's been optimized for telecom frequency, and we can then ride the wave of like 40 years of development of those protocols. We need to enact very low loss fiber to chip coupling. This is one of the things we're like laser focused on because it's very challenging. The challenge is essentially that the photon, when it lives in a chip, is a very confined mode. But the reason that the fiber is so low loss is because the mode expands. And so now you have like a mode mismatch. So the trick is not only there's physical things about alignment and things like this, but from a physics perspective, you need to do that mode matching between what is in the chip and what is in the fiber. And so it's not trivial that way. You also need very stable link controls, unlike telecom things. We don't kind of copy, so we don't kind of set multiple packets cannot be dropped kind of thing. That needs to be built in our correcting protocols. It means very tight specs. And we also need very low loss switch matrices to essentially be doing all of this routing, which is why we have been very focused on the optical switch. And that's it. Thank you.